Okay, I assume everyone can hear me. And let me just do a share screen here. So are there any questions right now? I guess we'll start out with that. Weird. Let's see, one second. One participant. Right, so. All right, so today what we're going to cover, and I'll just watch in the chat here if anybody has any comments or anything. Let's see, do I got record going? I think I do. Yeah. Okay. So yeah, it was weird. Participants are kind of, well, good. A little more now. Anyways, okay, now maybe now you guys can see my face also, in addition to the slides. All right, good. So let's start out now. All right, so last time we kind of rushed through the whole kind of structure of B+ trees, and we talked a little bit about extensible hashing, just kind of very, very briefly. Well, what we're going to cover now, we're just going to finish up this talk here and be a little more practical about how you actually use this stuff inside of PostgreSQL. And then also, by the way, just an announcement about recitation number 2. I'll be releasing that this afternoon. Okay, so I just wanted to do a little bit of touch up on it before I release it. And that addresses almost, or that is over this this material. So basically what we have here then is, well, mostly in PostgreSQL is just a B+ tree. So this B+ tree that we've been talking about is the dominant way that the indexing is done. There are some specialized ones, this gist index and this gin, and we'll cover those later when we talk about text search in a further lecture. But so for now, we'll skip those because there's some special indexing for text. So let's see here. So the way you declare indexes in PostgreSQL is you say create index, then you give it a name or not. I usually just say create index and I skip the name because it's just simpler that way. It'll give it an assigned name. And then you name the table and then the attribute. So this is the simplest way to declare indices. And let's see, I got to mute somebody here. Mute and mute. Okay. So what this will do is this will actually build a B+ tree index on that over that attribute. Now, when you declare things as primary key, it's automatically building these B+ tree indexes. So it automatically does that. So you can also drop indexes, and yeah. So this is kind of usually the way I do it: just create index on, and then give it the table and then the attribute. Or as we'll see later, attributes. You can have multiple attribute indexes. Okay, so there's also this, which is, I think the example here is not the greatest example because you would never use this. I mean, it would be very improbable you would use this. But there's the idea that what you'll do is you actually create like partial indices over the element, what's in the table. And actually the primary reason you do this, actually, or one of the primary reasons you do this is if you're ever going to kind of do a replication and you're going to do like there are some tools out there that allow you to set up partitions of tables, and then you can build an index over one just partition. So you could basically have it. So let's say that, for instance, we did the following. We said, I want to build it. I want to have this huge table of customers, and then I have like the city or let's say the land that they're in. And then what I can do is I can build a partial index over just Västerbotten. I can build a partial index over just Stockholm land. And then what I can do by doing that, what I can do is then I can actually split the table. I can do what's called sharding the table over separate servers and use replication. So what that allows for then is this is one of the techniques. It allows for you to have like a very scaled up system where when people from Stockholm access the contact or the customer information, they're going to go to one particular database, and then when they go to Västerbotten, they'll be accessing another. So partial indexes a lot of times are what's used to kind of build indexes for those partitions. But we'll see actually that there's going to be in recitation. Okay, recitation number 2 is going to be, I'm going to have you guys build these kind of galaxies of star systems, and it's going to randomly build these gigantic databases. So by the way, for recitation 2, you're going to need to install your own PostgreSQL database. You can't run it over the department's database, so you'll crash them because it's too big. But I'm going to actually have you guys build a partial index where you basically, given a single star, you want to basically build an index that will that's just the distance of the other stars to that one particular central star. So you'll see how that goes. That's kind of a transformed index. That's what that is. All right. You might have something like, okay, so basically what happens is that when you say, you can say inside here, so basically you say create index lower names, it's giving a name here, on student, and then you're applying a function to the actual search key value there, so that it's transforming all of them. That then could then be used in a query like this, where you're actually doing a comparison on the lower of the name. So the SQL, it's the query processor is smart enough to actually be able to bring those very specific indexes in when it's processing the query. So it's pretty powerful. All right, multi-attribute, sure. So what you can do is you can say basically, I want it to first. So notice one thing here. I can say create an index on student where it's going to take both the name and the department. What the structure of this actually is what it winds up doing is the first part of the index sorts on name and the second one on department. So this index is actually different than create index department name. That's so it does matter. The order does matter when you create these indexes, multi-attribute indexes. All right, so this is all just PostgreSQL syntax to do this. Now this is really powerful. So what this allows you to do is it allows you to recluster a relation based on an index. And so a lot of times you'll find that that doing this actually gives you real performance boosts. So you'll find that this actually can give you a boost in performance. So what this basically says right here is it says that you create an index SN on student, you're creating the name. So it's student name, I guess is the name of that. And then what you do is you basically say cluster student using the name of the index. So in this case, you actually have to use named indexes so that you can refer back to them on the cluster. So what this will do is this will reorder on disk, this will reorder the actual student table so that it's clustered on the name, the student name. So it's using the index to do the clustering. And what you'll find, I mean, that in particular cases, when you know kind of the types of queries are going to be asked, you'll find that being able to do this clustering can really give speed ups. So it's kind of worth knowing. And then you can have it so that there's the issue of reclustering. If you have a lot of inserts, updates, and deletes, inserts and deletes on a table will make it so it drifts from its cluster. So because it doesn't, it doesn't do everything well. It has to kind of put things at the end, and it as you know, if you do a lot of modifications of something, then if it was clustered on something, that'll actually tend to drift away. So what you want to do is you want to do recluster the table. That'll. There's another thing also you want to do is you want to do re-indexing. So that rebuilds the index. So these are both kind of maintenance procedures. These are usually those kind of things that run at 3 o'clock in the morning, just to kind of make it so that the database's performance doesn't degrade. Okay. And yeah, because these directives, what they do is they wind up locking the table. So that means that you got to do them at 3 o'clock in the morning, because what they're doing is they're going to lock out any other transactions from affecting the tables. So that's why they're run like that. Okay. All right. There's also what's called the fill factor. So if you recall, the basic definition of a B+ tree says that we had the order of the B+ tree, but the traditional definition was that the internal nodes, except for the root, all have to be 50% or more full. All right, and that's the same true with leaf nodes, where you actually have the records. They have to be 50% or more full. So that's called the fill factor. And that fill factor you can actually adjust in PostgreSQL. The current is actually 90, so it really asks for things to get packed in quite densely. And what that means is when the fill factor is at 90, what that means, it means that it's going to be a short kind of bushy tree that is going to kind of enhance performance. And it's going to enhance performance over in many dimensions. The downside of having a high fill factor like that is that as you add tuples in, and take tuples away, the requirements make it so that you might be making the index depth one larger or one fewer. And so sometimes if you have a lot of back and forth thrashing of inputs outputs, you want to have a lower fill factor so that it'll be less sensitive to doing this more expensive rebuild where you actually make the tree taller or shorter. Those tend to be kind of, you could be noticeable kind of blips in performance when that actually has to happen. So a lower fill factor will make it'll have it so that it's not as sensitive to that. Okay, so that, I think, don't worry about hash indexes. You'll never use these. You'll never actually create hash indexes on something. You would just rather do a B+ tree index. Gin and Gist we'll cover later. They're over a special type called the text string vector or text string query. So how do you decide which types of indices to try, and how does it evaluate performance? So this is like database tuning, and this is what recitation 2 is all about. So I'm going to try to have you guys play around with like creating indexes over this Galaxy schema to try to get better performance. So, to kind of get it to judge whether or not it's improving things. One second, let me see. I gotta. Oh, good. They muted themselves. So okay. All right. Okay. This database tuning stuff. So this is kind of a common thing that well, we're going to talk about this when we get to like the next topic now. So keep that in mind, that there is this big issue of like, oh, my queries my system is so sluggish because the queries are performing so badly. What do I do now? So that's a very common refrain for people in industry where they don't know what to do because the database is sluggish, and they're kind of scratching their head wondering, how do I fix this? And if you can, so there's a lot of work that goes around that that people are willing to pay for to optimize their queries, because obviously they need to have things move run quicker. So I think that we're going to cover some stuff that would help you kind of solve those kind of problems. So let's do that now when we talk about query processing. So now we have our indices built, and now what we're going to do is we're going to look at actually how this actually all gets kind of used to solve queries. And then with the assumption we want to solve queries quickly. All right, so, So how does it work? So how does like PostgreSQL or any SQL engine, how does it actually do its job? So what it does is it basically, SQL comes in, and then you have this kind of standard process that gets applied. So the first thing that comes in is just your raw SQL statements. Now, what'll happen then is that you'll have like basically a lexer, which basically turns. I mean, if you remember, I'm not sure how many of you guys have had a compiler course. I'm not gonna. That was a rhetorical question. I'm assuming that you guys have seen some of this before, at least. So the first thing you do is you tokenize the SQL. So you bust it down into tokens that are meaningful, and this can be a little tricky. So it's like, this is why, like, you try calling an SQL table, give it the table name constraint. It's not going to like it. So so basically there's already kind of at least some kind of reserved keywords where it's looking for that token. So you got to be that, but that'll have been blocked when you try to create a table called constraint. It won't let you do it because that's a reserved keyword. Anyways, what it will do is it will bust it into like values. It'll bust it into like reserved keywords, literals, and then also like table names, attribute names. That is essentially kind of what the tokenization looks like. All right, and then what it does is then it does a parse, right? So, and then when it does the parse of that, it generates a way to basically interpret that thing in an unambiguous way. So it kind of knows, it can map it to kind of internal objects inside of PostgreSQL. Then the next thing it does also is that if you have views, so if you're actually using views in your query expression, what it will do is it will just kind of plug in those definitions. And that's very elegant the way it does that. It just substitutes substitutes them in. Whatever, like when you say create view, the name of the view as, and then whatever that stuff is right there, it'll just substitute that in, all right, into the, it'll resolve that view so that it's kind of, it's as if it did the full lex and parse of that whole thing. So sometimes what it might actually do is it might just do after like the lexer, it might actually plug in the view definitions, and then, but it's probably not doing that because that'd be kind of a waste of rerunning the parser. You won't have to parse the view every time. So I'm sure they do it a bit more intelligently than that. But that's in principle what's happening. So like your real query is like the whole thing just with all the views expanded out. All right. So, but that can be a pretty sizable query. Now, what happens is that the when it resolved everything and it did so that's the lexer parser plus view resolver. So this basically, what this will give you in the end, or what plops out of this, is basically an expression in this, like if you recall from the database 1 course, we had this extended relational algebra. So it's basically an expression in that form, in the form of a tree. All right. So that is the query. That's the thing that if you execute it, you could actually just get, well, you can't execute it quite yet, but it's kind of like the relational algebra, extended relational algebra breakdown of what the query is asking. All right. So that's the input into the query optimizer. And that's actually what we're going to focus on today, is this query optimizer. So now that actual expression, or rather that relational algebra, extended relational algebra expression, can of course be using equivalence rules. You can rewrite that as something that would be more efficient to evaluate, right? So that's the central issue in terms of query optimization. That's the central task that it performs, is it transforms the relational algebra expression that came in, the extended relational algebra expression that came in, with one that is going to execute better, quicker, and that is also annotated with exactly which indexes to use, and what else would it have in there? Mostly which indexes to use, and then kind of, well, of course, there might be some other stuff in there, but it mostly would be like which indexes are going to be used. What are the actual parameters that are going to go into the actual operations that is going to actually give an answer to the query. And of course, that is what's called an execution plan. It's like a relational algebra expression with a little bit of annotation on it to say kind of how it wants the system to actually execute it. And this is where the indexes that you created are going to get plugged in along with algorithms that are going to use those indexes to actually get a much faster evaluation. Now, the last piece is the actual evaluation. So after you've done the planning, the whole thing, you kind of make the execution plan, then you've got to actually do it, right? And apply it as operations over the actual database tables, and then plop out an answer at the top. All right. So I hope that makes some sense. Just again, I'll watch from the chat here if there's any questions about that. So the lexer parser review resolver. Okay, we've kind of, this is kind of stuff that is kind of beyond the scope of the course, but it's fairly straightforward in the sense that, I mean, you can go look at the PostgreSQL's code that does this if you want. It's all in C. Now, this is where the real action is in terms of what we want to focus on here. So rewriting and then annotation. Those are the two steps. So I think I already talked about this, but yeah, we have the extended relational algebra expression, and then we're going to annotate it with exactly what algorithms we're going to use and which indices we're going to use. And then evaluation we'll cover just kind of in the end. There is kind of some interesting issues about evaluation, about like a parallel evaluation. So how do we use parallelism in the actual evaluation? Because that's nice if you can do it. All right. So now we're going to talk about basically this input extended relational algebra expression. So these expressions are like what they look like is they look like trees here, where the bottom is always going to be a relation. They get fed in to the relational algebra operator. So here's a select where we're saying basically we want the building to be Meet-Husit, and then we want to do a join for instructor to that. Now notice this might be the actual expression that came out of the analysis, where you basically are saying, give me the name, and then I want the building to be Meet-Husit, where I take of a department. Well, let's see here. No, this is the same thing. I'll come to this in a second. Okay, so basically, another way of doing this right here is we could actually compute the join of department and instructor, and then apply the selection over that. That would be a less efficient way. So we're going to come to kind of that in a second here. All right. All right. So the user of the database system is supposed to write some correct queries, right? Logically correct queries, but they should not optimize it, do the optimization of the SQL so that it executes efficiently. That should be the job of the optimizer. So really, you should be able to write any SQL expression you want, and the optimizer should transform that into, let's be idealistic here. It should transform that into the most efficient execution plan as possible, right? So in all the different equivalent, take the SQL, it maps it to like this extended relational algebra, and there are so many equivalent forms of that relational algebra. The query planner should find the most efficient and then execute that one. So you should be able to put it in any SQL, and it should be able to map it to whatever is equivalent, the most efficient executing version that's equivalent. That's kind of that's the way it's kind of presented as. That's kind of the hope. Now, in reality, that's not the way it works. In the reality, you got to be a little bit smart yourself about putting the proper. You'll find that the optimizer is not that smart. Sometimes it won't be able to find the right equivalent one. But if you just as a programmer thought a little bit and made your SQL kind of closer to the ideal one, or even at the ideal one, then the optimizer's task, it wouldn't have to kind of go searching all around to find it because it might miss it. So the optimizer is always sound in the sense that it never creates something that is incorrect rendition of the query, but it's not complete in that it will not explore the whole space of possible equivalent queries to what was put in to find the most efficient one. So that means it's up to you in reality, in the real world, it's up to you to also write your SQL so that it's close to the ideal one itself. And mostly what that means is you don't want to have sub-selects. You don't want to have like, you don't want to use exists, like where exists and then a separate select query, because that makes it very hard for the optimizer to kind of pull things out of that. Generally speaking, what you want to do is you want to make your from clause have all the relevant tables on that line, and that gives it a chance to kind of switch things around. So, but that's just kind of something you pick up in practice. All right. So, so the optimize. So let's just kind of deal with the ideal here. And the ideal is that it's going to transform it to something equivalent, and it's going to be looking at the sizes of the tables, right? So it's going to be looking at the sizes of the table, and it's going to look also to see what indexes are built on, over what attributes of the tables. And then it's going to basically make some kind of, it's going to do some kind of modeling of those parameters to basically determine what's the cost of this particular relational algebra expression. And it's going to say, if I have two relational algebra expressions and I have a cost model that says this one, this one here is much cheaper to evaluate, that's the one I'm going to pick when I go to evaluate, because I can only have one that I evaluate. All right. Well, for most database architectures, I believe that's the case. You always narrow it down to one. This is the one we're going to go ahead with and actually evaluate. So you want to have a model that will tell you how expensive it's going to be to actually evaluate it. All right, so here we are. This is the example I was trying to kind of get to before. So the SQL that comes in is select name, where we're going to have the department, natural join with the instructor, and I want the building, and the building, of course, is part of the department. I want that to be meet who's it. So just this might actually just produce the following. I guess you guys can see my pointer. The following relational algebra expression might be produced, where just get the name, select for meet who's it, and then we have the join, the natural join of department and instructor. However, this one is less efficient than this one here, because what you want to do is you want to try to push down the select. What you basically want is you want to have it so that you make sure the size of these things are as small as possible. And joins blow up the size of the result. So if you take two relations with and you do a join over them, most likely you're going to have something on the order of, n, if there's n tuples in one relation, m in the other, you're going to have something on the order of n times m big. So it's making things get bigger. Selections, however, are making things get smaller, right? Because you're filtering out lots of tuples. And projection is making things getting more narrow. So you want to push your projections and your selections down as far as possible, and then have your joins put off to the very end. Okay. Is that always true? No, but that's just a general heuristic. Okay. So we would like to be able to say this thing right here is equivalent to this, which it is. It doesn't matter what the state of the database is. These are always equivalent. But we would like to actually transform things into the thing on the right here, because that's actually going to be much more efficient to actually execute. Right? All right. So the way this gets done kind of in theory is via, and I have these posted. Let's see if I can actually rotate this silly thing. Oh, please rotate me. Yep, rotate, boink, and then rotate again. Boink, and then rotate one more time. Boink. There we are. And then we'll make this a little bigger here. All right, so I provide, this is from Silbershots. And no, yeah, it's from Silbershots. That's a different textbook. These are a set of these. This is not complete, like I said before, but these are all sound. So they are all correct equivalent statements of relational algebra expressions, but it does not characterize the full set of equivalences. Okay. Could you have it so that you characterize the full set of equivalences? I think you probably could. That's a question for the theoreticians. Yeah, I think that you could come up with a complete. You could, I think, in principle, come up with a complete set of equivalences. I think that's like Gödel's completeness there, essentially. But these are the ones, kind of the common practice ones, though. So they're all kind of like these kind of dry, kind of mathematical statements. Then they all would be, of course, accompanied by proofs. But once you have these, then you can plug these into your optimizer and have it so that it uses these to search for equivalent expressions. So this right here is just kind of an example of how, well, okay, like if you look at the way you use equivalence rules, this will show you basically how you can go from the input this and move it into that. And it's not so important, really. I mean, I hope that you guys just at least kind of in principle get a sense of that there is kind of a mathematical basis to this, that it's not just a bunch of hacking. All right, so there's kind of, this is kind of, there's a certain elegance to this. All right, so basically it's you're using these things. Now, as far as the way that the PostgreSQL actually implements this, is it doing it through a theorem proving kind of, now it's doing it probably through more of a, I think actually they use a genetic algorithm to kind of go through the equivalent. I think that they go and they, because I know that they're using a genetic algorithm to do query optimization. So I think what they do is they just basically have a set of equivalence rules, and what they do is they take a query and they perturb it in kind of a genetic algorithm thing. So it's kind of, it breeds, and they have a cost model that basically judges how much time is it going to take for this query to execute. And they search over the space of kind of reachability through these equivalence rules, if that makes sense. But I haven't, investigated so deeply how they're actually using genetic algorithms to do that. But I know they're using genetic algorithms. So every time you put a query into PostgreSQL, there's a little genetic algorithm that runs very quickly that kind of tests out a little population of equivalent queries for that, and then it selects the best predicted performance, right? And so that predicted performance is the notion of a cost model, right? That's the notion of plugging the thing into a model that is going to kind of grind out what's the cost of actually evaluating this query. All right, so this right here, by the way, is an example of something that it will not find. So look right here. We have, so you can put this into PostgreSQL and you can see if you want me to prove to you that it's incomplete, this is the proof right here. This is because to prove that it's incomplete, you just need one counterexample where you put this in and you show that it doesn't find the proper equivalent query. And that is when you have one query and you're intersecting with another query, right? Okay, well, this one here, give me the names of instructors where they're in computer science and their salary is over 70,000. That's equivalent to give me the people in computer science and let's intersect them with the names of the people who have a salary over 70,000. Right? These are equivalent. These will always be the same value result. but you'll find later that PostgreSQL will not be able, if you shove this one in here, the one on the right, it will not find the better, more efficient. So it's clear that this one on the left is more efficient from the point of view of evaluation, right? I mean, obviously, because you could have, I mean, who cares about the people over in biology? You don't want to have them kind of coming into this thing, and they'll get intersected out and won't make it into the final result because they're not in computer science. But here, it just does this as one pass through the table. So this is, I hope that people understand why this one on the left here is much more efficient than the one on the right. Okay. All right. So I think I already talked about this, like basically choosing a plan. So we have a bunch of equivalent ones, and then choosing one to evaluate. So what we need is we need a cost model. So we need a way to model how much it costs, what's the expense of doing these doing these operations. Now, the expense, as it turns out, is mostly determined in terms of the amount of seeks, the amount of seeks that it takes to the disk. That's kind of how you measure what the expense is of a query. So how many times do I have to like set that stupid disk head in motion to go snarfle up the next block? Right. I want to minimize the number of those when I'm doing an evaluation of a query. Right. That's what I want to minimize, because everything else, I mean, that takes an eon to move that stupid block, that stupid head reader, as composed to any kind of in-memory calculation takes nothing compared to that. Right. To compare it to moving that thing and then sucking the thing off of disk. So what it really comes down to is how many blocks does this thing have to suck off a disk? That's ultimately what you're trying to minimize. All right. Okay. So we have like, okay, so you can really kind of go down into the actual, determination of it, but that's essentially what the cost measure is doing. So now with an index, a lot of times what you'll do is you'll just make an assumption that the indexes are all in main memory, that the things that you're not, it's not always true. You could have like these really, really like absurd, but you can have these absurdly large cases where the index can't fit into main memory. That is, you're really talking like big data when you're talking about that. Well, you even have a worse case where the indexes can't even fit in main memory, right? So in other words, the index itself exceeds the size of main memory. That's like, I mean, that's like if you want to like track every single particle in the Milky Way galaxy or something. I mean, I mean, that's an insane amount of, I mean, we know we can't do that. We know we can't track every particle in the Milky Way galaxy, because kind of by definition, we can't track every, I mean, the number of particles, I mean, we have an upper limit based on the number of particles we can have in our computer system. So how can we track all the particles in the Milky Way galaxy, right? I mean, I'm assuming the particle, if we talk about like just an elementary, an atom, I think to store a bit or to store positional information, I mean, I feel it takes more atoms. Anyways, I hope you understand the infeasibility of tracking every particle in the Milky Way galaxy. But if you're going to track something obscene or absurd, like every single like GPS position of every human being in the last, 3 years on the planet, over every 10th of a second, that's considerably lower than the number of particles in the Milky Way galaxy. But if you're going to have that, and you're going to try to have an index over that, it may be that the index, probably is, that the index exceeds the size of main memory. So it's potentially possible. But in this case here, what I would like to just do is assume that the indexes all fit in main memory. And not only that, they are in main memory. All right, they're sitting there in main memory. So let's just make a more practical assumption. I think that's going to basically be true for most of the practical cases you're going to run into. So let's just assume that, okay? So really but now the actual files are going to be on they're not going to be in main memory. They're going to be on disk. Okay. So that's what we're just going to assume here. All right. So now what we're going to do here on the cost model is we're going to basically, all we're going to do is we're going to just look at the kind of the elementary operations and try to do a prediction of what the cost is of those. So the first thing we're going to do is we're going to look at selection. All right. We're going to look at selection. And the simple case where we're going to have equality on an attribute or inequality on an attribute or simple ranges. All right, so we'll just look at that. So basically something like select, select department, select in the SQL sense. Give me the departments where I'm basically doing a select clause, building equals meet who's it. That is a equality on a single value, single attribute. It's building and it's meet who's it. And that's the value, right? That's we're looking at that to try to model that out. All right. Then we can look a little bit at some, this is kind of getting beyond it here, but we can look at like something where we have conjunctions of those kind of conditions, or like where the building is meet who's it and the floor is for, right? That's a conjunction. Or we could have a disjunction where the building is meet who's it or the building is natural sciences, or negation where the building is not meet who's it. Okay, but these compound cases, let's kind of put those off for a second. Let's look at the real pure case where we just have equality, the building equals meet who's it. Okay. Now we're going to talk about the number of blocks in the relation. So how many blocks does this department table occupy? And the answer is, to be honest, 1 or maybe 2. Sorry, 3 maybe. I don't know. It's the thing is, it's kind of a stupid example because, how many departments are there? I mean, if you're talking about one university, but let's assume that we were talking about all the universities over the whole world or whatever. All right. So how many blocks does the actual relation contain? So we already know right there to say in the worst case scenario, we already know right off the bat. Let's say that there are 10 blocks, that this department relation has 10 blocks on disk. What's in the worst? And now we're saying we want the department name to equal meet who's. We want the building name to equal meet who's it. What's the worst case number of blocks we're going to need to suck in from disk? I tell you, I hope that just kind of everybody just says they're yelling at their computer right now, but they're all on mute, thank God. 10, Michael, 10. Okay, so it is 10, right? That's the worst case. I mean, we're just talking no index is nothing. Just going to snarf that thing up and look just down the line for every one of them that is in meet who's it. I say there's 10 blocks. Department relation is 10 blocks, and we have no indexes or anything else. And I say, give me the departments that are in meet who's it. I got to walk all the blocks, 10 blocks. Okay. So that's like index free, right? Now let's say, however, that we built a primary key index on building. All right. Then you would say, well, primary key index on building, we're not going to do that because it's not a primary key. No, what it is, it's basically it's a primary index. If I take let's say I take, all right, let's just kind of back away from here for a second. Let's just say instead, I want to say, give me the departments with the ID computer science, or ID, whatever ID corresponds to computer science. And we say there's 10 blocks that occupy let's say there's one block that we already have the indexes in memory. The indexes are in memory. I already told you that's an assumption. We have 10 blocks that constitute the department table. And it's clustered on the primary key. And the primary key is like some ID. Let's see, is that true? Well, I won't go back to it. Let's say the ID is 101, right? 1014 is the ID. Actually, I think 3700 is the ID of computer science, by the way. So let's use the real example. So if I have the department relation clustered on the primary key, and it's 10 blocks on disk, and I have the index, the B+ tree index that's over the primary key in memory, and I say, give me the department with ID equal to 3700, how many blocks am I pulling in from the disk? How many blocks? You can put the answer in the chat, but I'm assuming everybody is like yelling into their computer right now. Michael, you dumb. This is so obvious. It's 1, just 1. And that's right.
Because what it's going to do is first of all, it's a primary key. So there is only one tuple with 3700 as the value. And it's going to go down that index, and the index is main memory. So there's no need to grab any blocks there. And it's going to go down to the leaf, and that's going to point out to block number 7. And it's going to say, okay. And it's going to go and it's going to star fill up block number 7. And it knows that in block number 7, we have the record for the computer science department, right? Among others. But who cares? That's just slop left over. So there's some other departments that are next to computer science. Who really cares about them? All right. No, I'm sorry. I didn't mean to take a swipe at the other departments. But you know what I mean in context of the search. Okay. So there we are. So that right there is a case of A2. So that's a lot better. It's a lot better to just bring in 1 block than to bring in 10 blocks. And 10 blocks is not a very big table. Let's say it was 1,000 block table. Well, it's nicer to bring in 1 block than 1,000. Right? So this right here shows you that if you build, you're going to get these tremendous speed ups on when you're doing. I mean, it's pretty obvious, but I'm just trying to kind of paint it more more vividly. All right, so now let's go back now to the whole question of we're doing a search on the building Meet Husid. Okay, so in this case, let's say we cluster on that. So we recluster our whole department's table so that they're all clustered by the building they're located in. Okay, so now if I say, give me the departments in Meet Husid. Now, the point is that it's possible that is going to be more than 1 block, right? Because we might have just a ton of departments that are in Meet Husid, right? But at least what it's going to do is if it's going to have to find all the ones that are Meet Husid, it's going to find 2 consecutive blocks or the 3 consecutive blocks or however many consecutive blocks there are. It's going to use the index to locate those. So if it happens to be that the departments in Meet Husid occupy 3 blocks out of the 10 block relation, okay, so Meet Husid was very popular, then how many blocks is going to bring in when you have this kind of clustering index, which is not on a primary index, it's on a primary key. How many blocks it's going to bring in? It's going to bring in 3. So it's going to be smart just to bring in 3. So you're going to get a big win there as well. Even though it's not built on a primary key, although it is clustered on a non-key basically. But still, you can get big improvements there. But again, remember, you can only cluster on one thing. So once you cluster on one of the attributes, then you can't cluster on 2 attributes simultaneous unless maybe you copy the table. But Jesus Christ, you want to have terrible redundancy problems. But maybe there are cases when people do that. I mean, maybe, I don't know. All right, so now let's see here. We're looking at time here. I'm going to try to finish this up and kind of finish on a nice spot. Okay. So now we have a secondary B+ index on a key. Yeah, so secondary B+ index on a key. So let's say, for instance, we have department. Let's say we have a surrogate for. All right, what's a good example of a surrogate for? Let's just say that we have our contacts or all the people, all the students maybe, and they're all clustered on their Persona numbers. But then we also have email, and everybody has a unique email, and we build a secondary index on email. Now that secondary index has to be dense, right? So all the emails in the table have to appear in the index, right? It makes the index kind of get a little bit bloated. But now if we basically say, give me the student with this particular email address, that's a key, right? It's not a primary key, but it's basically a surrogate key. You call that a surrogate key because it can also, it's got unique on it, right? So you declare it as unique. And now that right there will take, if we have let's say we have 100 blocks that correspond to all the students, and then I have one particular email, it uses a secondary index. It finds a reference to it probably what it does, it finds reference to the actual Persona number. Then it uses the primary index to then find, oh, this is a reference to the block of that thing. That's kind of how it's probably going to do it. Now, that's all main memory. The indexes are in main memory. So all that's cheap, free, all right? And then it's going to basically just bring in one block, right? So the secondary index, the secondary index, I mean, the secondary index on a unique, basically, is also going to get major speed up when you're doing one single equivalent, one single probing for one single key value or unique key value. I hope that makes sense. All right, so I think what we'll do now, let me see here. Let's finish up on selection. We're going to go a little bit over, and then we'll come back at 20 after. So, yeah, okay, so that's kind of nice, right? So that's nice. So now if we talk about, we're going to extend this now to simple range queries. So now if we basically say we have a primary, so by the way, so what we are able to do here is we're able to kind of look at a particular use of a select. We're able to then go look at the number of blocks in a, we have a index, we have a select, we have the number of blocks in a table, and now we can predict, not perfectly because we have this issue of the second. Well, we can make some kind of statistical prediction. It's not perfect prediction, but in one case it is perfect. We can say one block, one block, one block. In the other cases, we don't know how many departments are going to be inside of, let's say, meet whosit. So we might have some kind of statistical distribution data that we can kind of predict the number of blocks the select is going to take. But the key here is that you look at the simple operation and you predict how many blocks this is going to take to calculate. So to achieve. All right. So if we look then at ranges, so inequality is well. First we'll look at range. So we're looking at all the things where like the value is greater than a certain amount. Then what in the case of a primary index, we can make kind of a pretty much an accurate calculation about how many blocks that will bring in. So if I basically say, give me all the Pearson numbers between this value and this value, just by looking at the index, you can predict how many blocks that's going to be, because when you go down, since it's clustered on Pearson number, you'll be able to kind of just snarfle up those kind of limited set of blocks. Secondary B plus tree index doesn't work out so well when it comes to that. In fact, it works out very badly. So because you don't know what blocks you don't know, like, so for instance, if I say, let's say I build a secondary index on let's say people's salary, the salary of people, and I have it, so basically I have it so that I have the secondary index. So if I say something like, well, give me the salaries between a certain amount and a certain amount, then it's going to wind up pointing down. It's going to wind up pointing to these buckets, or it's going to wind up pointing to these buckets that have pointers back to the Pearson numbers. But those then will distribute over all the kind of almost uniformly over all the buckets. So basically, it's going to wind up just kind of the worst case is it's going to bring in all the blocks. It's basically, in the worst case on a range on a secondary, it's going to bring in all the blocks of the table. That's your worst case. As it turns out, it doesn't always work out that way. It can be less because the range can be smaller, but in principle, it's just kind of going to you have no way to know which bucket it's going to bring in. I hope that makes sense, or which blocks it's going to bring in. This is kind of a subtle distinction, but it just kind of shows the limitation for ranges over secondary indexes. But one thing to say about that is that's true when you have such a dominating cost of bringing in blocks. But remember, as I said before, when we go to solid state devices, SSD, then basically this becomes less of an issue. All right, but if you're talking about disks, it's secondary indexes kind of break down on ranges. All right, conjunction, that might be like you have a set of conditions, and so then the thing is that what you want to find out is you want to find out which of these conditions should I apply at the level of the block access, of bringing blocks in, because the rest of them I can just apply when it's in main memory. So you would of course want to have the one that's the most discriminative. So if I said something like, give me the people that live in Umeå that are male, that are over the age of 40, then I'm thinking, if we think about Sweden, which condition is the best one to use when we go out to access the tuples? Think about that. People who live in Umeå, who are male and are over the age of 40. It's pretty clear if you think about it that the most discriminative is the one people living in Umeå, because that one is going to, I mean, 5 million for the male thing, over the age of 40, God only knows. Maybe another 5 or 6 million or something in Sweden, right? But Umeå, we're down to like 100,000 something, right? So apply that one, because that'll then make it so that you can just apply that one as they bring in the 100,000 tuples, then you can apply the other ones on those tuples, rather than bringing everybody's over the age of 40 and then, that's dumb, right? So the most discriminative, so you need to have some statistics about the distribution of tuples over the underlying database, and that's kind of maintained in the catalog. Okay. So that's basically how you will kind of deal with the conjunction. There are some other ways to do conjunction where you're taking, if you have multiple indexes, you can do conjunction where you're basically doing pointer intersections, but that may or may not be there. Disjunction is kind of always going to be a loser. I mean, it's tough. There's not much you can do about disjunction. Although with disjunction, you can, if you have indexes built over all these things, you can then do pointer unioning. So, I mean, if the system can actually go to the indexes and figure out everything over the indexes, and then kind of have like a composite thing where these are all the pointers to the actual tuples, and then go out to disk, that's actually kind of a big win. So playing around with the indexes is a big thing that would happen in a query optimizer, or in an execution plan, because it would basically say which algorithm are we going to use to do that. All right, so that was pretty quick, I suppose. I hope that people, I mean, when this stuff is actually pretty useful to know this stuff. So, but it's not probably the most tasty stuff. I mean, it's kind of, maybe, I don't know. Maybe some people might think it's boring. I don't know, but I'm excited by it. So, anyways, all right. So now let's just take our break and be back at 20 after. So we want to get through this pile today. So back at 20 after. I'll put any questions in the chat, and I'll pause the record.
Okay, everyone. Assume we're back here. Screen share. Can people hear me? I'm assuming. Yeah. All right. Let's go. Okay. So now we're going to move on to projection. So we've done selection. So clearly we have, what do we have left? We have projection, we have joins, or the products, Cartesian products, or natural, all the basic join operators. And then what else do we have? Then we are going to also have like order by. We're going to have stuff like distinct. We're going to have, okay, so we're going to basically add in all the basic operators into the mix. So let's just do it then. Okay, so projection. So when you're doing projection, well, it's always good to apply. It makes things thinner, right? It kind of reduces it's making things smaller, so it's good to apply. But projection. So depending on if the query is using distinct, if you project, so for instance, if you say that you want to get like all the building names, so project building name over departments, then basically if you're going to say if you're going to not say distinct, and you're just going to say project so you're going to get duplicates in that result, then it's easier to handle, because you're not going to do anything. You're just going to pass things through, right? The projection is just going to be an operator that just takes a stream of records coming in, and it pushes out a stream of records going out, albeit the stream of records going out are thinner based on the projection, right? Okay, so that's fine. But if you said select distinct department, then what it needs to do is it starts needing to pull things up in main memory or on disk if it gets really large. But it starts needing to it needs to keep a structure around to check for duplicates, right? That's what it winds up requiring. That's what it winds up requiring. Obviously, one sec. Seems like a nice sunny day. Finally. All right. So then we have the issue of dealing with duplicates, and I think that probably we've all kind of experienced this a little bit in programming languages. So how do you deal with duplicates in general? Just think about it. You have a hash structure, and you just start throwing things into the hash table. And then if you, so I'm a projection operator.
I'm doing it distinct. Give me some of the query that's being asked is select the distinct buildings over the departments. I come to the first one, it's Meet Husid. Okay, I can report that back, right? So I'm not blocked. Like I don't have to do a whole bunch of calculation where I can't report anything to the next operator in the sequence. I can actually just stream or iterate my results through, because I just say, okay, fine. But now I'm keeping a structure on the side, and I come to the next department, which is also in Meet Husid, and I don't report that back because it would be a duplicate. And the query above was asking for a distinct on the projection. All right. So this requires then to have some kind of hash. So on the fly, yeah, I mean, I'm going to get rid of this. I mean, you want to do it with hashes. So basically what you wind up doing is you wind up just doing a hash, building a hash table. Just have a hash table that you're building up in main memory. And if it's already in the hash, then don't report it if you're doing distinct. All right, I hope that's clear. Yeah, and this is, by the way, the reason, because under bag semantics, why you have to say distinct, because it's an operation that costs something. All right, in terms of memory, it costs something in terms of memory. Remember, like, okay, so in databases, like one of the definitions of the database is that these intermediate results, a database is not a database unless it can handle intermediate results that are larger than main memory. That's kind of maybe one of the definitions of an actual database. I think something like SQLite doesn't do that though. So there are, but like PostgreSQL would. So if you ask for something like project the distinct addresses of all the people in Sweden, let's say that whatever hash table that was being built up is larger than the main memory you have available, then the engine has to be smart enough to be able to have it so that kind of gets parts of that hash table get put out to disk, so that it can, that it can perform it, but it doesn't, because databases by definition are dealing with big data, large amounts of data. So you have to have it so that the assumption is that intermediate representations on the way toward evaluating a query can actually can exceed main memory, right? So this is something it definitely complicates the algorithms and the implementation. So. All right. So now, okay, so that was all we wanted to say about projection. So projection is fairly straightforward. But now we're going to deal with joins. All right, so joins are the big ones. So joins are the ones where we really get a payoff if we have indexes built. Let's say that we're going to do a join over two tables, and okay, if we're doing a join over two tables, and then again make the database assumption that these tables are larger than main memory, that you can't bring both these tables into main memory, then let's say that you're going to be you're doing a join on attribute A of R1 and on A of R2. Okay, and there are no keys built. There's no indexes built. These are not keys, or there's no indexes built over these attributes. Now, if you were being exceedingly stupid, you would do this on a tuple by tuple basis. In which case, but no one would ever do that. You wouldn't be that dumb. What you would do instead is you would do it as a block. So again, this is the worst case scenario for a join. Well, this actually is the worst case, but no one would ever be that stupid to implement it this way. So this is your true worst case for a join. That is that we have a certain number of blocks that R1 occupies, and a certain number of blocks that R2 occupies. And the way we calculate the join is we take the first block and all the tuples in that block of R1, and then we take the first block of R2 and all the tuples in those blocks, and we do a join. We basically match them together if they have the equivalent value on attribute A, and then we append that into some kind of result set. Okay, and so what we do is if we have 10 blocks in let's say we have 100 blocks in R1 and we have 10 blocks in R2, then we're going to have the total number of block combinations is going to be 1,000 block combination, right? So if for instance, I mean, it's not really the way it works, but if this one here was like 1,000,000 blocks and this one here was 1,000 blocks, you could probably fit R2 in main memory. But let's say we're being stupid when we don't, and then basically we have 1,000,000 times 1,000, so we wind up getting 1 billion block accesses to actually compute the join. Now, what's nice about join is non-blocking. So as we're kind of finding these matches, we can report them upstairs to whoever was asking for them. Because remember, all these operations are put together in a big tree. And so what my inputs are, and when when I do the match and I find two things that are joining, I can then just pop that up to the output above me, and that becomes the input to the operator that's above me, or one of the inputs to the operator above me. So joins are nice in the sense that you can do it iteratively. So as you find the results, you can immediately pop them up to who was calling for them. So that's kind of nice. Notice there are certain operations like sort by. If you want to think of something that isn't like that, it's like something where you're going to do a sort because you don't know what the thing is going to be. If I have to sort by name, I come across the name Aardvark. I'm not sure if that's the first one. It probably is because it's double A for Aardvark, but there might be something even more before that, and I have to go through the whole thing to see that. Before, so ordering is a blocking, or it blocks the. It's not iterable. You don't iterate on an order by. So that's an example. So that would be, you couldn't just do that way. But anyways, this would be an extremely stupid way. I mean, well, this would be an extremely stupid way of doing it, which you would never do. But this is the way that you would do it if you had no indexes and you had to compute the join. All right, you just do this basically block-oriented nested loop join. And I believe that you can see that in PostgreSQL. It'll give that name when you actually ask for the explanations of the query plans. All right, let's say we have a different kind of join where we have an index on one of the relations. So which we have, R2 here has an index on A. Well, then it's pretty clear. So we have an index, and then we don't specify what type of index. But anyways, we have some index we have an index on the attribute A. We don't have an index on the attribute A here. So it's pretty clear what our strategy is going to be. We're going to do a block-oriented traverse. We're going to basically go through this thing basically as a table scan, essentially. It's not really a table scan, but it's basically, we're going to go through all the blocks of this table. And every time we come to an A here, we're going to use the index to find the corresponding tuples over here, and then we'll be able to compute the match that way, right? So we have one side has an index on it, so clearly we want to go down the other, we want to do the search on the other side in terms of computing for the index. Now that's true if under certain statistical assumptions, but let's say that we have, I mean, it might be though that like if you have something like, see, would that ever be the case? I think it's almost going to be always the case. I'm just thinking if there might be like, if this one is a giant relation, this one's a very small relation, there might be some way you would like if this was a really, really dinky little relation, you might even skip using the index, right? If this only occupies one block, the relation 2, well, then what good is the index? All right, but anyways, the point mostly is that for the most of the case, you'll walk through the one that doesn't have the index, and you'll just do the matches using the index, because then you'll get basically n log. You'll get kind of an analysis of an n log n, right? Because you're going through these n here on the n1 tuples, or it's usually done in terms of blocks on the R1, and then for each of those, you're doing a log-based access to get that. And then of course, this log-based access, because it's a P plus tree, is log-based, 200 or something, 300. So it's really, it's almost, it's practically constant time. Okay. All right. That's okay. Now we have an even better situation where we have a merge join, and the merge join is the case in which we have indexes built on both. We have indexes built for both attributes. And I guess the ideal here would be that they're both, it's clustered on A in both cases. So we have, if R1 is clustered on A and R2 is clustered on A, we're really going to get we're just going to basically merge them together, essentially. So we're going to get something that is going to be on the order of the number of tuples in R1 plus the number of tuples in R2. So merge joins, if you can get you can get merge joins to work, you get really pretty dramatic performance boosts. The hybrid merge join, what do we want to say about that? That has to do with, okay, vectors ordered on A, that we have a secondary. So this was primary indices. So this the pure merge join is we have primary indices on both, so it's clustered on that attribute. So then it's just really, you just kind of walk through things very quickly. The hybrid merge join is that you have a secondary index on A. This is kind of more likely to come up in practice. You have a secondary index on, so a lot of times what you'll do, this is actually really common, you'll see this. And in fact, I think some systems will actually do this automatically for you. But foreign keys, a lot of times you'll find yourself building indexes on a foreign key. But they'll always be secondary indexes, or most of the time be secondary indexes. So you'll get a hybrid merge join if you use those. So basically what that will do is it'll walk through, in terms of block access, let me see, do we get an analysis here? Yeah, I mean, you get something close to a merge join, but it could be a little bit worse in the sense that it could be, I mean, you could suffer all the things that we talked about before with secondary indexes. But if you see a hybrid merge join being used, so the system could recognize and sees the indexes, then usually you're going to get a big win out of that. Then you have the double hybrid merge join where they're both on secondary indexes, and these, of course, these are all just kind of not as good as the pure merge join. All right, there's this kind of notion of using a hash join. I think, I can't remember what they call it when you do the explain analyze inside of PostgreSQL. We'll come to that. But this is a very common way in which the merges get, you use hashes to basically, what you wind up doing is you wind up, if you're going to be merging on A here, what you wind up, so doing an equijoin here, merging on A, what you wind up doing is you wind up basically hashing everything in R2 and everything in R1, you hash them into the same, the bucket address, you map them into a shared buckets. So if I have some particular value for the attribute A in one relation and in the other relation, and if I am just going through and creating hash indexes on both of the relations, but what I'm doing is I'm merging them together. So when a tuple in relation R2 gets hashed into a particular address, it winds up landing in a bucket that a tuple from R1 that also has the same value of A, it also lands in that same bucket. And inside that bucket, they're joined, right? So that's the notion. The notion is that the hashing function is allowing you to do the match, essentially. All right, it's allowing you to compute the ones that will match, because the value A is going to match the value A, and if you are mapping them to the same joint bucket, then you see them come together, then you say, okay, that's a match, right? Now it might be that there's other things in that bucket, like let's say the D happens to map into the same bucket, and then you have an A over here that maps in the same bucket. Well, you won't going to match those because you're going to look at them and say, no, well, the A and the D are different. So there's no join. So it has to be a little bit of extra calculation there to compute the joins, but you're doing it to set the granularity of the buckets, and you get these, then, and based on that, you get to, you get some pretty dramatic speed ups. Let's see. We could probably figure out what the complexity is. Strictly speaking, the complexity in terms of the number of buckets is it's going to be the complexity in terms of the number of blocks is going to be the number of blocks in R1 plus the number of blocks in R2 in terms of disk access. That's what it's going to cost you to do a hash join. Assuming that all those buckets can fit in main memory. If they can't all fit in main memory, then the amount of blocks are going to go up because you're going to have to shunt them back and forth. But yeah, so I hope that makes some sense. So these hash joins are a pretty steady technique. And then what's nice about the hash join is the hash join doesn't. You're building this kind of index on the fly, so it doesn't require. It's going to. Yeah, which kind of leads to the question of why would you ever use if you have hash join, why would you ever use a nested loop join? All right, so a nested loop join, you're definitely going to have to use a nested loop join if it's a theta join. So if you have less than, I want to join and where I'm doing a calculation of the receivables is greater than the invoice amount or something like that. So it's not doing equimatch, it's doing a theta join. So that would, you can't use hash join on that. but you'd have to use and if you don't have indexes built, you're going to have to use the nested loop join on that. Yeah. So that's really the hard part of it, or the complex part of it, was the joins and how the joins come in. So you see there's a set of different join algorithms that can be used. So you'll find out later that you can actually see which one gets picked. And usually this is where you're really looking for when you try to optimize your queries, like which join on using which indexes, which algorithm was used. And then you say, well, why isn't it being used? And then you start wrestling with the thing and you kind of fiddle with the thing. And then, oh, finally, now I got the damn thing to work. That's the life of somebody doing query optimization. They say, well, this SQL form doesn't kick it in the right way, but I rewrite it myself. Screw the optimizer, it can't do anything. And then, oh, now I look and I see that it's doing it right. Okay. Set operations, union, intersection, difference. Yeah, so these are all going to kind of be using some, kind of hash techniques as well. So like the intersection, take two sets, I'm going to intersect them. They better both be in. I do like a kind of a hash join type strategy where I'm going to have these buckets and I'm going to check them and see that they got to be in. They both have to map to the bucket to get into the result. And then similar kind of thing with difference. One of them has to map to the bucket, the other one must not map to the bucket. And then so basically you just hash everything into buckets and you do the calculation over the buckets to get the results. Let's see, differencing. We can think about the differencing for a second. So what about hash difference? So difference is if you think about that in the nature of its blocking, it's kind of blocked until it's got all the values for the so I say blocked. I try to not say block because it confuses it with block, but to be blocked means that it's not an iterable operation. Set difference is not iterable in the following sense, that it can't start supplying any values until it's at least materialized or gotten all the results on the difference part, on the part that can't be part of the solution. All right, so that's so we have order by and we have difference. We have two things that are blocking. That is that they're not iterable. Union, intersection, union, intersection, okay. Set operations via hashing, I think I just kind of talked about that. Aggregation, the big thing with aggregation is to compute the groups. So you do the partition based on the group. So that definitely suggests a hashing strategy where things are kind of all the elements in a particular group are going to, you map them to a certain hash bucket. And then you do a little bit of refinement to make sure that they're not, you map them to a hash bucket and then you keep them in the hash bucket. And then later on, when you do the calculation of the aggregation, you go to the hash bucket and do it from there and make sure that they're actually matching specifically inside the bucket. You can also do the aggregation on the fly so that as you're putting things into the bucket, then you're actually tallying a value. So like the sum or the count. And even the average, you can get out by, kind of doing it as a iterative. You're doing it as on the fly as you're putting the values into the buckets. All right, good. So finally, so now it looks like we're in pretty good shape here. Okay, let's keep on going then. All right, good. So that essentially covered the main strategies about how the query, how the execution plans kind of bring in indexes and bring in different types of strategies to compute these things quickly. Now we're going to talk about evaluation. So the evaluation, the normal kind of easy way of evaluation is something like PostgreSQL. I'm not really exactly sure. I kind of look into that because you can fiddle with that. But something like SQLite is probably just going to have the simplest version, which is kind of this demand-driven pipelining. So what that basically means, let's just see if I have a nice graphic here. Not really. Think of it this way. So in pipeline evaluation, partial results are, if it's iterable, partial results are passed up the tree so the operators further up in the tree can start doing their work. All right. Now, this is almost all, since everything is multi-core now, we almost always want to have pipeline. All right. We almost always want to have pipeline rather than some kind of thing that stupidly traverses from the leaves up to and doing only the calculation at the leaves and then going up to the root. What you would really want to do is start the calculation on each node inside the tree. And then a lot of the calculations are just waiting for something to get passed up. And if they're iterable or they're non-blocking, they do their work as things come in, and they keep on passing them up to the top. So then you get good utilization of all the processors, and you get better performance, quite simply. Now, if you're in that kind of evaluation method, then you have two options. One option is that you're going to do this kind of lazy evaluation, so that basically that you only, if you're an operator, you only are going to give results out if the operator above you is asking for them. So if the iterator is called to give out the next result, then you're going to give it out. Right? It's easier to implement it that way than to do what's a producer-driven pipelining, where what you're doing is you're just doing all your work and you're filling up a buffer so that you're done with your work. And then later on, when they start asking from above, you just kind of start passing them back. You pass back the thing in bulk, basically. You just kind of grab from the buffer and pass it back. So the idea of kind of filling up a buffer with all your work, and then when it gets requested from above, then just supply that, that's producer-driven. Okay, so the producer can do all their work, and then they can be done with their work and then go do something else, and then just have that buffer left over just to pass up. That's much harder to implement. It's a much more sophisticated algorithm, and you have a lot more checks and stuff like that to do it that way. I don't really know what PostgreSQL is, to be honest, what the status is. I know they have a lot of parallelism type stuff going on, but I'm pretty sure they're demand driven. But they might have. Of course, there's probably hybrids between these two, but of course, ultimately, you want to get to something where you're doing this producer-driven pipelining if you really want to squeeze performance out. All right. So this is just kind of reiterating those points. What do we got here? Oh, good. So we're in pretty good time here. I can probably do the file. Okay. All right. So what this right here is just talking about is like what things are iterable and what things are blocked until they get done, like order by is blocked. All right, so we get to this right here. So you're going to be using this a lot in recitation 2, and I'm going to cover recitation 2, or just the draft of recitation 2. I'm going to cover that with the extra time we have here because we've kind of made some good time. But let's just start out right here. All right, so you have the explain directive, and what the explain directive does is it actually just gives you the query plan. So this plan right here. So if we look right here, so it says explain, select name from instructor, where the department name is computer science and salaries is greater than 70,000. So what it's doing here is it's doing a sequential scan on instructor. And this cost here, so this is it'll report back this plan. So you try to read these kind of plans here. What it basically does is it says the cost is going to be this first number here. That's like the cost to start it up. So this is the cost it's going to take before it can return anything, right? But in this case, it doesn't have any startup costs. It doesn't have any costs where it's going to take time to actually do something first before it actually starts doing the work. And so in principle, it could pass back a tuple immediately. All right. This right here is its estimated total cost. Now these units of cost here are just kind of like funny units. They don't really correspond to anything. I think there was some kind of loose correspondence, but they're basically meaningless. So it's not 16.6 seconds. It's more like 16.6 times something, some factor seconds. This is the predicted number of rows that are going to come back. It's kind of interesting that it did that. And this is the width. That is like how, what it is. You're doing select name. So the width is going to be 58 bytes, apparently. That's what it's, I don't know what that was declared as. Here's the filter. So it's going to do a sequential scan. When it does a sequential scan, it's going to do what's called a filter, which is basically a select. And that filter is going to basically be that the salary has to be greater than that, and the department name needs to be computer science. All right, now this right here is the other the equivalent version of the query that was using intersecting two queries. So here it's doing basically it's just basically, let's see, do we have anything interesting to say here?
the append, I don't remember what that does. So these are kind of internal things to PostgreSQL, but basically it's doing a sequential scan to get all the computer science instructors and a sequential scan to get all the people with salary over 70,000. Notice here, it did a prediction here that it's going to be 147 rows that are going to come back on this. And it's at two rows coming back with computer science. So I guess, I mean, in this particular case here, there wasn't much in that. I mean, I don't know how accurate these are. It might be kind of interesting to look and see how accurate these are when you look, but because these are predictions. But anyways, the key point here, of course, one of the key points is that it's doing a different plan for two equivalent queries. So it's not finding anything. And this one's predicted to be 32, and the other one was predicted to be 16. So this one is more efficient. It's predicted to be more efficient. Let's see if I want to say anything else about this. So it's doing a hash set operation here of the intersect. So it's using hashes to do intersection when it brings these together. So it's a hash set operator. And now we see here we have a hash join operator. So what is it doing here? It's saying, give me the names of the departments where the building is Watson and the salary is greater than. Give me the names of the departments. It looks like it's the name of the department. No, it's the instructor name. Give me the instructor name. So departments don't have names. The instructors have names. Give me the okay, basically, give me the instructors in the Watson building, where the department is housed in the Watson building, who have a salary greater than 70,000. That's what this is doing. So if you look kind of more into this right here, it's basically saying, we go down to the bottom here, and it looks like it's doing a sequential scan on department, looking for the Watson building, which is what you would expect. So in there, it is. So you notice right here, it's going to take like, it's predicting it's going to take that 16.75 second time units, whatever, to do that. And it's going to return, it predicts 3 rows are going to come back from that. That's its prediction. Then actually, in this case, it's not a prediction. I'm sorry, well, explain select. No, this is a prediction. 12 rows here is the actual number of rows here. This is kind of the silly thing coming from PostgreSQL. All right, so it's doing a sequential scan of department to find those. Then it gives out so you notice right here what it's doing, which is kind of nice. It's actually, okay, so output is, it's doing a hash here. Let's see, how is this doing this? The building name equals Watson. And the output is the department name. Yes, exactly. So what it's doing here is it was pretty smart actually about going down to this sequential scan here, and then actually going through and doing an extra projection and plucking out just the department name. And then not only doing that, but also doing a hash operation so that it removes the duplicates, because it doesn't want to have extra duplicates because it's going to be doing a join, right? It wants to make it as small as possible. So that's what this thing right here is doing. So the whole output from this thing right here is just going to be the 3 departments, apparently. The 2 rows, actually, in this case, or 3 rows, that are in the Watson building. All right. Now, it's got that out, and it wanted to get this. It wanted to do this full calculation here and to remove the duplicates and all that. It wanted to do all of that in time before it did the actual join. So notice here that the cost here is that's the minimum, because it needs to have this calculated before it starts in on the join. Now then there's a sequential scan here where it's just looking for the people over 70,000, whatever. It's predicting 147 rows for that. And now it's going to be doing the join, and that does a hash join. It winds up doing a hash join with 1 loop, which is good, and it predicts 3 rows coming back. Okay, so I hope this gives you an idea of kind of like, you can read these things and see kind of what it's doing, and you'll see like the different names that pop up here, and you'll get kind of a sense of as to what they correspond to in terms of like the theory that was presented today. Let's see here. All right, and then we just have the a similar one what we're doing in inspect. I'm not really sure. Again, it's gonna be more costly. It's not being smart enough about doing the about pushing the intersects together. All right, so that's I hope that makes sense. I'm looking now at the chat. I kind of missed that. I didn't look for a while. So again, questions if you have them. All right, so now let me go over to, and I haven't published this yet, but I want to at least show you guys what I'm thinking. I'm going to probably make a modification to it. In fact, I'm not probably going to make a modification to it. I'm going to make a modification to it. So I should probably turn off record at this point because I don't want you guys to, but I'll be posting this later today. All right, recitation 2 is split into 2 different parts. And I'm probably going to reduce this one because I don't want, I'm going to do something with this. But the big Broham, that has to do with this kind of model of tracking individuals with those like foot things. And it has to do with calculate what could be the minimum maximum height. So this is kind of what's using that kind of that mathematical model that was developed in the slides. Just to kind of get you in there and to kind of get a little bit used to doing some of these kind of calculations. But I'm going to probably try to simplify it down and try to make it more coherent, make it more coherent with respect to PostgreSQL. So in other words, I want to try to figure out I want to get a little bit better idea of what PostgreSQL is actually doing, what it really does, as opposed to what it could be doing based on theory, and then kind of make the proper assumptions here so that it guides it more toward real world case. So that's kind of, as I trick around with this, I'm going to kind of just be modifying there. But basically, it has to do with like, we have a set of individuals we're tracking with GPS, each measurement, and then it basically says, this is kind of giving you the size of the records. So each individual is getting like a record of they have an ID for themselves, and they have a GPS signal, which is getting reported on a particular timestamp, and it's collecting the data every minute. Mostly to see if they drift out of where they're supposed to be. I personally believe this is the future of criminal justice. It's just sorry. I mean, I shouldn't joke, but I mean, if you're going to be a criminal, then I think you lose your right to have, and it's cheaper to keep people at home, and there's good reasons. If they have enemies, though, you have to make sure that their enemies don't come in contact. That's a key thing, because we want to keep them separated so they don't continue the cycle of violence, kind of thing. What do we have here? So basically, this is just kind of give you some assumptions here, and it's this idea of kind of tracking these and what are the kind of system assumptions, and then how big are the indexes? How big do the indexes become in the worst case? In the best case, how short are they in the best case? And it kind of lets you kind of get a real world kind of feel for something. And it shows you the eminent feasibility of tracking, 10,000 people for 100 days. Yeah, so you can do this with a laptop in principle, basically. I mean, maybe the network traffic, I was getting a little bit into the network traffic. I might take that away. Okay, anyways, this is the more juicy one here, because this one we're actually going to, it's not just a paper example. This one here is, this is a quote out of 2001. Basically, what I want you guys to do is to take this code here, where we have planets, stars, and wormholes, and I want you to kind of copy this into your PostgreSQL, but your PostgreSQL, not the department's PostgreSQL. Again, this will cause trouble if you run it on the department's. And then what this is doing is we have an idea of a planet, a wormhole, which is 2 stars, like a star that you start with and a star that you end with, because you have to kind of go close to the star. And then for some kind of tricky relativistic gravity thing, it pulls you and then sends you to the next star as a warp. But you need the big gravity of both those endpoints. You can't just kind of create one of these things out of thin air. A wormhole has to have a big star next to it, right? That's how it works. Am I right or am I right about that? I mean, you can't just have. If I make a wormhole just out in the backyard here, then no. It's got to be close to the sun. You got to come in at a certain angle, and it'll slingshot you somewhere else, like faster than the speed of light. All right. And then we have planets that are circling stars, and the planets can have several, is there life on the planet? Is there civilization? All right. With this, right? Okay. So what basically, these are some functions that kind of create a random, galaxy. So you make planets around stars. You make a solar system, which is a star with a bunch of planets. and then you make galaxies here. So these are all functions that are kind of just you're just going to wind up running these things, and then you make wormholes inner. Oh yeah, that's right. Because I don't know what I was doing there with that wormhole thing. Wormhole start. They have risks. There's always a risk going through a wormhole. I mean, because you might just get turned into muck, you know. But you know, if you want to, what did I do? This is stupid. Michael, what'd you do, you dumb dumb? I didn't put everything in here, or did I? All right, so here's how it works. Actually, now I realize what I did. All right, so you're going to load this thing in here, and then you're going to say this. You're going to basically say make galaxy, and this is a small little dwarf galaxy with 10 million stars. So what this is going to do is it's going to call the function make galaxy, which is going to make just a ton of stars randomly distributed with a ton of different planets around them. And then what's cool is that in there, just to kind of like tell you about this, there's always a chance that one of the planets is fairly unlikely, but you got like you get like a 1% chance if random. What? That can't be right. Make a planet. Oh, I'm sorry. Random generates a number between 0 and 1. So yeah, if it's 1% of the time, random is going to be greater than 0.99. If that's the case, then life is going to be true. So the planet is going to be, there's going to be life on the planet. Then 1 out of every 10,000 times the planet, you're going to wind up getting civilization, right? So some kind of civilized type is going to evolve. And then after those, this is what's cool. After those, 1 out of 1,000 of those civilizations, life goes away, but civilization is still there. And that's basically a robot civilization. That's a civilization that's just robots, right? Because they went through a life stage maybe, but then they got rid of all the life and now they're just robot, okay? So I think I found one of my planets in a giant solar galaxy I created had robot civilization. So it's pretty cool if you actually wind up with robot civilization in your galaxy. Anyways, enough of that. And then we have different types of stars and blah blah blah. And this will just generate like just a giganto database. So, like I said, don't run it on the department servers. You could explain to Strict that you build a galaxy of 10 million stars or 20 million stars, and then he's wondering why the printer doesn't work anymore, or something else that would happen, like the scheduling system busts down because somebody created a galaxy. So these are the queries I want you guys to ask. So like, give me the okay, so what's explain, analyze. So that'll give you, not only will it, so I want you to declare indexes over this thing to improve the performance of these queries. So stars with spectral type O and number of planets equals to 3. That doesn't make any sense. I think I want you to get the count. Like how many stars with spectral type O and number of planets equal to 3? Type O or the number of planets equals 3. These are just count queries. Did I make that clear? I don't know. Okay. Declaring indexes and tailoring. Okay. I want the number of stars. I'll put this in. I'll update this. The number of stars within 80 light years of star 1. The number of planets with a civilization. The 10 nearest civilization pairs with their star pair and distances. Okay. So it can be a pretty complicated join. So anyways, this is going to be over big data. And I want you guys to like fiddle around and get the best performance you possibly can. And then when we do recitation, we'll compare people's kind of performance and their strategies to kind of get these things to run properly. So I hope that, this should be fun, I think. I mean, I wish I could do this, but I can't. So, or I can, but well, it seems like it would be fun. All right, guys, I hope that makes sense. So yeah, so this makes indexing this kind of stuff at least kind of cosmic rather than just boring. I mean, if it was just like a student database, it's like, ugh. So. All right, guys, if there's any questions, put them here. Otherwise, look forward to a notification that this has been released, and that'll come later today. Okay. Oh yeah, one last thing about projects. So actually, one project group is already kind of cleared with me. So if you want to meet with me, just say when. Otherwise, we'll meet on Friday, but we don't have to meet on Friday. We can, this is Zoom. These are Zoom times, so we can move it. And we can meet whenever. It makes it easy for everybody. But I want to talk to every project and kind of like I had a great meeting yesterday with the one project, and because they have a really nice setup, and we kind of arrived at that. So I think we can do that with the other ones as well. So look forward to hearing from you guys when you want to speak, meet with me, and blah blah blah. All right, good. If there's not any questions, then let's leave it at that. So I'll see you all, and then I'll stop recording.